Introduction to Ensemble Learning. Ensemble learning addresses the limitations of single decision trees by combining multiple models to improve overall performance. The core idea is that a group of weak learners can form a strong learner when combined properly. Weak learners are simple models that perform only slightly better than random guessing. When properly combined, they form a strong learner with high predictive accuracy. Decision trees are particularly effective in ensemble methods. They're fast to train, handle different data types naturally, and have high variance, making them ideal building blocks for ensemble methods. There are several main approaches to ensemble learning. Bagging trains models on random subsets of data to reduce variance. Boosting builds models sequentially, focusing on previous mistakes to reduce bias. Stacking combines predictions from different models using a meta-learner. Ensemble learning offers several important benefits. It significantly improves prediction accuracy and generalization. It reduces overfitting, provides robustness against outliers, and handles missing data better than single models. Ensemble methods transform simple decision trees into powerful predictive models. By combining multiple trees, we address the limitations of single trees while enhancing their strengths. Bagging, or bootstrap aggregating, is a powerful ensemble technique that combines multiple decision trees. Bagging is short for bootstrap aggregating. It combines multiple models trained on different random subsets of the training data. The key idea is to train many trees on different samples of data, then combine their predictions to create a more robust model. Bootstrap sampling creates multiple training sets by randomly sampling the original data with replacement. With replacement means that the same data point can appear multiple times in a sample. This creates diverse data sets that help capture different patterns. The key difference from regular sampling is that points can be selected multiple times, allowing each bootstrap sample to be unique. Each bootstrap sample is used to train a separate decision tree, leading to a diverse set of models. Since each tree is trained on a different subset of the data, they learn different patterns and make different mistakes. This diversity is what makes bagging powerful. It helps the ensemble overcome the limitations of any single tree. After training, predictions from all trees are combined through voting for classification problems or averaging for regression problems. This aggregation process helps reduce variance and creates a more stable and accurate model than any individual tree. Bagging provides several key benefits. It reduces variance, helps prevent overfitting, and creates more stable models that perform better on new data. Bagging forms the foundation for more advanced ensemble methods like random forests and is widely used in applications ranging from medical diagnosis to financial prediction. In this section, we'll explore how bagging reduces variance in decision trees. Individual decision trees suffer from high variance. This means they tend to overfit to their specific training data. Small changes in the training data can lead to significantly different tree structures. This results in unstable predictions, making individual trees less reliable for new data. Bagging, or bootstrap aggregating, works by creating multiple datasets through bootstrap sampling. Each bootstrap sample is created by randomly selecting data points with replacement from the original dataset. We then train a separate decision tree on each bootstrap sample, resulting in slightly different trees. Finally, we average the predictions from all these trees to get our final prediction. Let's explore the mathematical intuition behind why bagging reduces variance. The variance of the average of n independent variables is 1 over n times the variance of an individual variable. For example, if 3 trees make errors in different directions, these errors tend to cancel each other out. When we average their predictions, the errors often cancel out, resulting in a more accurate overall prediction. Let's visually compare a single decision tree's boundary with a bagged ensemble's boundary. A single decision tree creates a jagged decision boundary that closely fits the training data, but may not generalize well. In contrast, a bagged ensemble produces a smoother boundary by averaging multiple trees, reducing overfitting. This smoother boundary is less sensitive to small changes in the training data, demonstrating how bagging effectively reduces variance. To summarize what we've learned about how bagging reduces variance. Bagging creates multiple trees from bootstrap samples of the training data. By averaging predictions, the variance is reduced proportionally to the number of trees. When trees make errors in different directions, these errors tend to cancel each other out in the final prediction. The result is smoother decision boundaries that generalize better to new, unseen data. Random forests extend the bagging concept by adding an additional layer of randomness. In standard bagging, each decision tree is built using a bootstrap sample, but all available features are considered at every split. Random forests add another layer of randomness. At each node split, only a random subset of features is considered. Typically, we use the square root of the total number of features. This feature randomization further decorrelates the trees. Since each tree only sees a subset of features at each split, they're forced to consider different relationships in the data. This seemingly simple modification significantly improves performance. By building trees that focus on different aspects of the data, random forests create a more robust ensemble that generalizes better to unseen data. The combination of bootstrap sampling from bagging with random feature selection makes random forests one of the most powerful and widely used ensemble methods. Random forests not only provide powerful predictions, but also offer insights into which features are most important for those predictions. This feature importance measure adds a layer of interpretability to what would otherwise be a complex black box model. To understand feature importance, we need to look at how random forests make decisions. Each tree in the forest uses different features to split data at each node. Feature importance is calculated by measuring how much each feature reduces impurity when used for splitting across all trees in the forest. Features that consistently create good splits across many trees will have higher importance scores. The calculation of feature importance follows a systematic process. First, we track how much each feature decreases impurity when used for splitting. Then, we sum these decreases, weighted by the number of samples affected. Next, we average these sums across all trees in the forest. Finally, we normalize the values to get percentages that are easier to interpret. Feature importance is typically visualized as a bar chart, ranking features from most to least important. Interpreting feature importance provides valuable insights from your random forest model. It helps identify which features are truly driving predictions. You can detect redundant or irrelevant features that add little value. These insights guide feature engineering efforts to improve your model. Ultimately, feature importance helps you understand underlying patterns in your data. Let's look at a practical example. In a customer churn prediction model, feature importance revealed that contract length and monthly charges were the most significant predictors of whether customers would leave the service. This insight allows the business to focus retention strategies on short-term contracts and pricing structure rather than less impactful factors. Gradient boosting machines represent a powerful ensemble technique that builds models sequentially. Gradient boosting machines, or GBMs, are sequential ensemble methods that combine weak learners to create a strong predictor by minimizing errors through gradient descent optimization. In GBMs, we use weak learners, typically shallow decision trees that individually have low prediction power. The gradient boosting process starts with an initial prediction, typically a simple constant value. The difference between the initial prediction and the actual values gives us the residuals. In step 2, we train a new weak learner to predict these residuals. In step 3, we update our prediction by adding the new model's output scaled by a learning rate. The GBM algorithm follows a specific mathematical formulation. We start with an initial prediction f0, which minimizes the loss function. Each new model, FM, is built by adding a new weak learner HM to the previous model, scaled by the learning rate eta. Each weak learner is trained to minimize the loss function for the residuals of the previous model. Gradient boosting uses gradient descent optimization to minimize the error. This process moves iteratively toward the minimum of the loss function. Each iteration of the gradient boosting algorithm takes a step in the negative gradient direction, reducing the overall error. This follows the standard gradient descent update rule, where parameters are adjusted in the direction of steepest descent of the loss function. Gradient boosting machines offer several key advantages over other ensemble methods. They typically provide high prediction accuracy and can handle various loss functions to address different problems. GBMs also perform implicit feature selection and work well for both regression and classification tasks. Gradient boosting is widely used in various applications, from web search ranking to credit risk assessment, customer churn prediction, and fraud detection. XGBoost, or extreme gradient boosting, has revolutionized the field of machine learning. It has won numerous competitions and became one of the most widely used algorithms for structured data. XGBoost enhances traditional gradient boosting in several important ways. First, it introduces regularization terms that help prevent overfitting by penalizing model complexity. Second, XGBoost implements more efficient split-finding algorithms, significantly speeding up tree construction. Finally, it provides built-in approaches for handling missing values, a common challenge in real-world datasets. XGBoost builds decision trees using a greedy approach. Let's visualize how it works. At each step, XGBoost optimizes a loss function with regularization terms. This ensures the tree structure is both accurate and not overly complex. Let's compare XGBoost with other modern boosting implementations. XGBoost is a general-purpose algorithm with regularization and efficient split finding. It works well with most structured data problems. LightGBM uses a leaf-wise growth strategy and supports GPU acceleration, making it particularly fast for large datasets. CapBoost excels with categorical features and requires less hyperparameter tuning, making it ideal for production systems. Modern boosting implementations offer significant performance advantages over traditional gradient boosting methods. Traditional gradient boosting machines provide our baseline performance. XGBoost significantly improves performance through its optimized algorithms. LightGBM further enhances speed and efficiency through its leaf-wise growth strategy. CapBoost provides additional improvements, especially for datasets with categorical features. Let's summarize what we've learned about modern boosting implementations. Let's compare bagging and boosting to understand when to use each approach. Bagging and boosting differ fundamentally in their approach. Bagging trains models in parallel on random subsets, with each model having equal weight. Boosting trains models sequentially, focusing on errors from previous models. Bagging primarily reduces variance. It's effective when your base models tend to overfit the training data. Boosting, on the other hand, reduces both bias and variance. It can correct errors made by previous models and improve overall performance. When should you choose bagging? It's ideal when your base models tend to overfit. Your data has high variability. You need robust out-of-bag error estimation, or when computational efficiency is important. Boosting, on the other hand, is better when your base models are too simple with high bias, when you need the highest possible accuracy, when your data has low noise, or when computation time is not a constraint. Let's consider some important trade-offs between bagging and boosting. Bagging is less likely to overfit and can be easily parallelized, but may have high bias if base models are too simple. Boosting typically achieves better overall accuracy and handles both bias and variance, but can overfit with noisy data. Here's a practical guideline for selecting between bagging and boosting. Start with random forest as a baseline. If performance is inadequate, try boosting. With noisy data, stick with bagging. With clean data and when high accuracy is needed, use boosting. And for explainability, bagging may be preferred.